Hi everyone. In today's video, I am going to be laying and covering the basic foundation of calculus. Basically, the method of how we find the gradient of a single point on a curvature or the rate of change through a technique which is called differentiation. I'm sure many of you have heard of it. From what I have heard and from my experience, this basic logic of how we achieve the technique of differentiation is either not explained that well by teachers or they just straight up skip it and teach the thing called the power rule as the first part of this chapter, even though the first part of any mathematical chapter or topic should be its logic, not a rule.
Boring.
Okay, so you, the viewers, are one of two people. Either you've never studied differentiation and this is your first encounter at it, and if so, then well, you're lucky.
Look at this dude.
Or you're the other kind of people who have studied differentiation in school or college and learnt its techniques but never really understood what it was about.
Because you never even gave attention in class. You were having fun in class, making memories with your friends. All you wanted to do was to go home and play video games, or just chill in bed, or hang out with your friends.
Or if you're a girl, just do girl things. Do makeup and take selfies, I guess.
I was just kidding. Come on. Come on. You guys know I was just kidding, right?
You're a disgrace to the human race. You should be banished from society and ashamed of yourselves, never to be
Okay, now let's take a very simple curve with the equation y equals to x squared. This is a quadratic curve, also known as a parabola. And on this curve, let's take one point whose x coordinate would be called x itself. Why do I call it x? Well, it is because this x is the x coordinate of a random point on this whole curve. It could be here, or here, or here, or here, or anywhere. But on this curve, of course, but I've just randomly taken it as here for convenience. As the x coordinate of this random point is x, and if this point lies on the curve of y equals to x square, wouldn't the y coordinate of this point be x square? As the coordinates are written as x comma y, I've let the x in the coordinate remain as x, but just replace the y in the coordinate with x square, because on this whole curve, the y is equals to the x square. If this x was 2, the y would be x square, which would be 4. If this x was 5, the y would again be x square, which would be
21.
You stupid.
25.
okay. So this other point that we are taking, its x coordinate would be called x plus delta x. Now why is that? Well, this expression basically tells us that the x coordinate of this point is delta x more ahead of the first point's x. For example, the first point's x was 2 and the delta x between these 2 points was 3. Then the second coordinate's x coordinate would be 2 plus 3, hence resulting in 5.
Quick math.
And just like the first coordinate, the x comma x square, the y coordinate of this point on this curve would be given by the square of the x coordinate, right? And the x coordinate here is x plus delta x. Hence, the y coordinate would be x plus delta x whole square. Now, before moving ahead, I would just like to replace the delta x with a random letter. Let's say h. Why? Well, ahead when we are going to be doing calculations, the delta x with x would become very confusing.
I am confusion.
Okay, so if I were to make a line connecting these two coordinates on the curve, the gradient of this line would be the average gradient, or in better words, the average rate of change of these 2 points. This line that tells the average rate of change of 2 points is known as the secant line. Not to be confused with the reciprocal trigonometric function sec, the abbreviation for secant. That is a completely different thing. Now, as the formula of the gradient of a straight line is m equals to delta y over delta x, m is the common symbol for gradient, you can say. or known as y2 minus y1 over x2 minus x1 by some people. By the way, I prefer the delta form as it is more condensed and also looks better, looks good. Okay, so let's apply this formula to find the average rate of change of these 2 points, basically the gradient of this secant line. Let's write down both the coordinates first, x comma x square and x plus h comma x plus h whole square. From this we can see x is x1, x square is y1, x plus h is x2 and x plus h whole square is y2. After putting them into the gradients formula, we get x plus h whole square minus x square over x plus h minus x. Let's expand each of the brackets first. Next, we bring x square and x close together and cancel them out. After that, we are remaining with 2xh plus h square over h. We bring h common out of the numerator and then cancel it out with the denominator, by which we are left with 2x plus h as the gradients equation of the secant. As we used the variables x and h in this, which could be anything, we can now find the average rate of change between any 2 points on this curve by inputting the x and h, where h is basically the delta x, the change in x between the 2 coordinates. For example, let's take 2 points on the curve, 4,16 and 9,81. As the second coordinate's x coordinate is bigger than the first, we already know that here for the secant formula, x is 4 and x plus h is 9. We can find h by subtracting both, of course, which gives us 9 minus 4 equals to 5. Now, as we know the x and h, let's input both in this to find the secant's gradient of the 2 points on this specific curve known as y equals to x squared. Side note, each curve has its own secant gradient formula, which is found out by the working I told you a bit before. Now we just input x and h into the gradients equation, which gives us 2 into 4 plus 5, 8 plus 5, 13 as the gradient of the secant line between the coordinates 4,16 and 9,81 on the curve y equals to x squared. Again, the gradient is 13. Now you might be wondering, why did I do all these long calculations and form the equation of a secant's gradient when I could have just directly applied delta y over delta x, which would have given us the same answer as that? Well, firstly, I did it just to prove to you that the secant's gradient equation is indeed correct, as both it and delta y over delta x are giving the same answer, thus correct answer. Secondly, and more importantly, I did it just so I can finally introduce the concept of differentiation to find the gradient of a point's tangent through the secant's gradient equation. Okay, so now I'll start to move this coordinate. I'll start moving it closer and closer to this coordinate, and the closer it gets, the closer the gradient of the secant to the gradient of the tangent of the point itself. Soon, this coordinate would become so infinitely close to this coordinate that the delta x or h would become very infinitely small, and when we would look from our perspective, it would just seem like there is a single point there, even though there would be two, but two that are infinitely close to each other. The minuity of h is such an important value in calculus that without it, differentiation cannot even take place in the first place. And if differentiation can't even take place in the first place, the whole theory of calculus and its studies collapse, as differentiation is an integral part to all of it. Hence, if we calculate the gradient of the secant between these 2 points, we are basically calculating the gradient of the tangent of this point itself. Because, they are infinitely close. But how do we do that, you may ask? That's where the secant gradient equation comes in. And through differentiation, the secant gradient equation turns itself into a tangent gradient equation, dy over dx. It basically changes from delta y over delta x, which is the secant gradient equation, into dy over dx, which is the tangent gradient equation, because of an infinitely small value. H is basically 0.00000
Several days later.
0.000000000
One eternity later.
0.000000000 add infinity. I'll keep saying 0 for infinity. That's how small h is. But there will be a 1 at the end to make it a value, non-zero value. H is basically very close to 0 but not at 0.
ディオ。ほう、向かってくるのか。逃げずにこのディオに近づいてくるのか。
And so that's why in this equation we will just eliminate h and anything being multiplied by h, because the value will be so small that it is just basically negligible. That's how small it is. It's just negligible. Hence, after eliminating every h and h multiplicate in this equation, we are left with 2x. And in 2x, if we input the original x coordinate, we would get the gradient of the secant line between it and another infinitely close point, or just a better way to say it, we would get the gradient of the tangent at that point itself. If x was 3, then the gradient of its tangent would be 2x. 2 into 3, 6. 6 would be the value of the gradient.
Wow.
And now at the end we have found out that the gradient of any point on the curve y equals to x square would be found by dy over dx equals to 2x. No, we are not done yet. I yet have to tell you how the power rule is formed. It's not just by thinking that I could just bring the power of x square down to make it the 2x and I have achieved the power ruler. No, there is a whole working behind it of how we go from x to the power n to nx to the power n minus 1. A whole working. Let's just say this is a random curve with an equation in the format of y equals to x to the power n, or contains terms in it that are in the format of x to the power n. These are two coordinates whose x coordinates would be the same as before, x and x plus h. Hence, the y coordinates would be x to the power n and x plus h to the power n, because they lie on the curve of y equals to x to the power n in the format of that. Now, by applying delta y over delta x, we can make the secant's gradient equation of this curve. Let's do that. Let's write down the two coordinates first, x comma x to the power n and x plus h comma whole bracket x plus h to the power n. By putting them in delta y over delta x, we get x plus h to the power n minus x to the power n over x plus h minus x. Next, we're going to expand each bracket, but what about the bracket x plus h to the whole power n? Well, we are going to apply binomial expansion in it. By doing that, we get x to the power n plus nc1 h to the power 1 x to the power n minus 1 plus nc2 h to the power 2 x to the power n minus 2, and then it goes on. We don't know how far it will go on because we don't know the value of n. And then at the end there will be the negative x to the power n that we input in the original gradient formula. as the numerator contains a positive x to the power n and a negative x to the power n, they both cancel out, which leaves us with nc1 h x to the power n minus 1 plus nc2 h square x to the power n minus 2 dot dot dot, and in the denominator a singular h. The answer of any value c1 is always any value. What do I mean by that? If I were to say 6c1, the answer of that would be 6. If I were to say 20c1, the answer to that would be 20. Just like that, as here it is nc1, the answer to this would be n itself. So it becomes n h x to the power n minus 1 plus for nc2 we have to do long factorial calculations, so I am going to leave it as that nc2 h square x to the power n minus 2 plus dot dot dot, and in the denominator a singular h once again. So now in the numerator, any value that occurs after nc2 h square x to the power n minus 2 will also contain an h, right? An increasing power of h. Next it's going to be h cube, then h to the power 4, then h to the power 5, and so on. So that's why if we take h common out of the numerator, the other terms will still have an h in them, right? Except the first term, because the first term contains the first power of h to the power 1. So if we take h common out of the numerator, only the first term is left with no h. And then when you cancel out the h in the numerator and the denominator, we are left with nx to the power n minus 1 plus nc2 h x to the power n minus 2, and so on. Any value so on will have one less power of h. Now that we have the secant gradient equation, we bring the two coordinates infinitely close to each other, resulting in h to become infinitely small, subsequently making every term having h in it to get neglected, leaving us the term independent of h, which is found to be n multiplied by x to the power n minus 1. We observe that when we bring two coordinates infinitely close to each other on any curve in the format of, or any term in the format of x to the power n, the point's gradient or the point's tangent's gradient is found through n multiplied by x to the power n minus 1, and hence we have just found the most simplest yet heaviest rule of differentiation, namely the power rule, that once again the derivative of a term in the format of x to the power n is nx to the power n minus 1, and then the derivative tells us the gradient for any point on the curve. So the logic behind differentiation is not the power rule, it's the working, that we find a secant gradient equation and then convert it into a tangent gradient equation. That working, that's the logic behind differentiation, not the power rule. The power rule is just a rule for any term in the format of x to the power n. One last thing is that dy over dx is not equal to delta y over delta x, but rather dy over dx equals to delta y over delta x only and only when one condition is being fulfilled. What is that condition? That delta x is infinitely close to 0. Only then dy over dx will be equal to delta y over delta x. What I just said right now had the concept of limits being applied in it. Limits is a completely different topic that I don't think I have time to get into right now, and I don't want to go off on a tangent. Okay. And there you have it. The logic behind how differentiation happens and the formation of the power rule, the basic foundation of calculus. You know, this is my first YouTube video. I might have said very fast somewhere or very loud somewhere or something like that. So please do tell me so I can work on myself and not do that later on. Goodbye everyone and assalamu alaikum.